So let's jump right into it. We're going to look at some guided examples here just to give you an idea of how we use the disk method in calculus to find the volume of a solid. So you can see the visuals and you have them in your notes. We have the square root of x, and that function is going from 0 to 9, as they say in the example. It's also bounded by y equals 0, which is the x-axis. So we have this region. Let me just draw a quick little enlarged sketch here. If that's 9, we have this region right here, and we're rotating that region around the x-axis. All this is stated in the problem. So when we get into the idea of a cylindrical disk, we have to kind of visualize the three-dimensional idea, and you can see that in this picture right here. And so if this disk is going to be used, then the radius of it, kind of think about what's going on here, right? Okay, the radius is just from the x-axis out to the curve, and that obviously dictates how large the disk is. So for that reason, and we remember kind of some of the things we talked about in our investigation, the volume here is always pi r squared h, right, of a cylinder. So we have pi from a lower bound to an upper bound, and then we have this radius function, we call it, and that's squared. So in this example, right, our setup looks like this, where we have pi on the outside, we're going from 0 to 9, and the function itself is the radius, and we have to square that. And so this is really the hardest part right here, just getting that set up, because if we can do that, integrating it really isn't that bad. And if we were to go ahead and do the workout, right, the pi is a constant, so it just hangs out for a little bit. We're really integrating x, because when you square the square root function, you just get x. And so that just brings us here, x squared over 2. Got that pi outside hanging out here. So we can evaluate that from 0 to 9 and then multiply by pi. So we should wind up with 81 pi over 2. You may have a question about units. Right now, there's no units involved only because no units were presented. So we don't have to say things like inches cubed or centimeters cubed. In the case of a problem where that's true, then obviously we'd want to note that. Let's look at another example. So again, you have example 2 in your notes, and you can see this time we're dealing with the function 1 over x, but this one we couldn't go from 0 to something because it's undefined at 0. So they're asking us to go from 1 to 2. So think of it like this, a little region in here being rotated, and if you kind of just think of it three-dimensionally, right, let's use a different color here. There's your cylindrical disk right there. You can see a little bit better in the 3D model. So again, what's the setup, right? Well, volume equals pi. Here we're going from 1 to 2 times the radius, so in other words, the function squared. So most times what you want to do in these cases is you would like to make the integrand a little bit nicer to deal with. So this is 1 over x squared, or x to the negative 2. That's just easier to integrate, right? So when we integrate that, we have x to the negative 1 over negative 1, or, right, negative pi, and then we can evaluate 1 over x from 1 to 2. And when you do that, you should wind up with pi over 2. So the general idea here is we want to continue to see this pattern. The pattern is the pi is a constant outside, the cylindrical region being represented by pi r squared h. H really is dx, that's the width of each disk added up. And then r, the radius, is actually the function. And that will continue to be a little bit more complex as we progress, but for now, it really is just the distance from the x-axis to the function itself. Okay, so just one washer method example I think would be a good one, just to kind of get us thinking just slightly differently. I think you really have to hone in here on the 2D picture. So we have the square root function, and then we have, let's use a different color here, we have the x squared function, right? So you have this region in here, right in there, right? And the key here, and this is really, really important, is how do I know not to use the disk method? Well, the cylindrical disks that are going to be formed here are going to be formed with some vacant space between the region itself and the x-axis. So that calls for, that's almost like the donut example. That there's a little hole going on here. So if you think of it, again, three-dimensionally like that, there is a giant hole in the middle right here, right? So when we look at the radius function now has to be a difference of what we call the outer function right there, outer radius, and then the inner function, which is x squared. So I think one of the things that's helpful here is to just note which one's which. So we usually use capital R for the outer radius, and that is the function that is farther from the axis of revolution. So in this case, square root of x. We use lowercase x for the function that is closer to the axis of revolution. And so in this case, it's x squared. So what does our setup look like? All right, well, again, we have the pi. The difference here is, and again, they're telling us, they're showing us that they intersect at a specific spot. That happens to be at 1, 1. So that tells me that I'm going from 0 to 1. But I have to make sure I show the outer radius squared minus the inner radius squared. So that it's not the two of them, it's not the difference squared, it's each individual function squared. So what does that look like when we input our functions, right? So we have the square root function squared, that's the outer radius, and then we have the x squared quantity squared. That is the inner radius. So like even the disk problems, that's the hard part right there. Let's circle that up. Getting there is the hardest part, because after that, it just becomes a question of integrating and maybe saying it a little nicer or writing it a little bit more user-friendly. So I would definitely do that. I would probably just call this x minus x to the fourth. Keep it simple. And nice easy integral to do there. So we have x squared over 2 minus x to the fifth over 5. We're going to evaluate that from 0 to 1. And so I'll let you do the math there. You can always pause the video if we're going a little too fast. But your final answer should be 3 pi over 10. So this is just kind of, again, for instance, a guided idea. The next video will go into a little bit more depth on some other examples, and you can kind of start to see the progression.